Hi, and welcome back to our AP Chem flipped classroom, where today we're discussing spectroscopy and spectrometry. So we're looking at mass spectrometry and photoelectron spectroscopy. So we have spectrometry and spectroscopy. They are slightly different. Mass spectrometry provides atomic and molar mass data as it ionizes a compound and then splits it up based on mass charge balance. And photoelectron spectroscopy provides data about the energy that's required for ionization and for applications thereof. So we're going to start with mass spectroscopy. This is really where all of our information comes about the masses of individual isotopes, and also when we talk about finding molar mass for molecular formulas, often that comes from this data as well. So mass spectrometry, it is based on a mass to charge ratio. So we'll take a look in a minute at a diagram of how a mass spectrometer works, but it basically charges the molecule or element, and then it bends it around a curve. And so we get a mass to charge ratio, which we can then transform into a mass. So when we're looking at the spectrum that we get from mass spectrometry, the relative size of the peaks in the spectrum indicates the relative number of particles that have that mass. And so it actually separates the isotopes according to their mass, and it's used to find the relative abundance and the atomic or molar mass of unknown substances. And so when we talk about calculating the mass of the average atomic mass of an element, where we look at the abundance and the mass of the individual isotopes, this is where that data is coming from. So how does it work? So we have several different parts. The first is the ionizing chamber. And so we place our sample in, we superheat it or charge it with electricity, we send it through an electron beam, and that is what gives it the charge. So we're applying a negative charge. Then we send it through an accelerator, and it goes through a bent magnetic field. So depending on how charged that particle is, the charge to the mass ratio, the heavier ions are not going to bend as much, the lighter ions are going to bend more, and the other ions are going to go straight through. And so what we see is this peak of these peaks, these spectra, that give us an indication of how many of the more bent, less bent, and central that we have. And so mass spectroscopy is going to give us a spectrum that looks like this one, where we have a higher signal intensity for chlorine 35 and a lower signal intensity for chlorine 37. And so because we have two isotopes, we have two peaks, the relative amount of each isotope is indicated by height, so the signal intensity. So because we have more chlorine 35 than chlorine 37, we have a much higher peak for chlorine 35. And we can compare these peaks to get numeric values, which in the case of chlorine is 75.77% chlorine and 24.23% chlorine 37. So we can use this information to calculate that average atomic mass. So we're going to take the relative abundance of each isotope, multiply that by the mass of the isotope, add them up, and we're going to get average atomic mass. So given the data from the previous slide, which was 75.77% chlorine 35 and 24.23% chlorine 37, remember, convert this to a decimal, multiply 35 by the 0.7577, 37 by the 0.2423, add them up, and that should give you the average atomic mass of chlorine, which is 35.453 grams per mole. Okay, so how does this come out in AP style questions? So this is a AP multiple choice questions. The elements iodine and tellurium have similar average atomic masses. The sample was believed to be a mixture of iodine and tellurium, was run through a mass spectrometer, and this is the spectrum that we got. Now notice that this one's been converted into a bar graph rather than the spectrum that we saw on the last one. Either one is perfectly acceptable. Sometimes you'll see spectra that are straight lines. It's all giving us the same information: relative abundance on the y-axis, mass number on the x-axis. So it says, which would be the best basis for concluding that the sample was pure tellurium? And then it gives us some choices. So tellurium forms ions with a negative charge, whereas iodine forms ions with a -1 charge. Well, that's irrelevant to this information. All of the information we have is mass information, not ionic charge information. Tellurium is more abundant than iodine in the universe. Again, totally irrelevant to our question. Iodine consists of only one naturally occurring isotope with 74 neutrons, whereas tellurium has more than one isotope, or iodine has a higher first ionization energy than tellurium does. So honestly, this is one of those AP questions where you can kind of just rule out all of the wrong answers, A, B, and D. You're not expected to know that iodine consists of only one naturally occurring isotope. But given that the other three are wrong, and if that's true, then we would expect to see only one peak, and we definitely have more than one peak. So C is our answer. Okay, I'm going to move again. All right, so based on the mass spectrum of atom Y, which of the following statements is false? So we've put atom Y into the mass spectrometer and we've run it. And we're asked to find out which of the following statements is false, based only on this mass spectrum. So peak A and peak D, we have mass numbers and we have relative abundances. There are 7 isotopes of atom Y. So 1, 2, 3, 4, 5, 6, 7. We have 7 peaks. So certainly that would fit with B. Peak C comes from the most abundant isotope of atom Y. Certainly that is the highest one that we see. And peak D comes from an atom with 4 more protons than the atom that gave peak B. So while this mass differs by 4, if it were protons, that would be a different element. So D is certainly wrong. Peak A and peak D come from atoms that have the same number of electrons. Well, we don't have that information from the mass spectrum. On the other hand, the piece of information that we do have from this spectrum is that C is the most abundant isotope because it has the highest relative number of atoms. Okay, so we'll go over this one together in class. It's asking us to figure out the mass spectrum of the element antimony is most likely represented by which of the following. So I want you to think about it. Which of these has the same average atomic mass as antimony? Okay, and again, we'll do those together. All right, let's talk about photoelectron spectroscopy. So we've moved from spectrometry to spectroscopy. Small minor difference, but let's be technically correct. So spectroscopy allows us to identify atoms and molecules based on their electron distribution and the energy of that electron distribution. So we're going to be asked to interpret photoelectron spectra to determine electron configuration, as well as some information about the interactions between the electrons and the nucleus. So first, what is it? So photoelectron spectroscopy is a lab technique that measures the relative energies of electrons in atoms or molecules. So it basically works by kicking electrons out using high energy electromagnetic radiation and then measuring the kinetic energy of those electrons. So we're seeing how much energy we put in and what energy those electrons have when they go out. And the difference between the two is the amount of energy required to remove that electron. So photoionization, we're ionizing through light. So why do we do photoelectron spectroscopy? Because this is the lab or experimental or empirical basis for the things that we understand and assume about electron configuration. These differences in energy levels, how do we know that a 4F is a higher energy level than a 6S but lower than 5D? Because we literally can measure how much energy it requires to remove this 4F electron. So this is our experimental basis. So if we look at how photoelectron spectroscopy works, we have our atom, we hit it with high energy electromagnetic radiation, usually X-rays, and we know that the energy that goes in is equal to Planck's constant times the velocity of that photon. And when that hits with that amount of energy, it kicks an electron out. And we can measure the energy, the kinetic energy. We measure the velocity of that electron. We know the kinetic energy is 1/2 mv squared. So we can measure the kinetic energy, well, not directly measure, we can measure the velocity and determine the kinetic energy. And the difference between the two is the ionization energy or the ionizing energy of that particular electron. The difference between this and ionization energy is that we're not just talking about removing 1 or 2 electrons, but we're talking about removing all the electrons from an atom and comparing how much energy it takes to remove those various electrons. So this is an example of a spectrum that we would get from photoelectron spectroscopy. The peaks are relative to each other. So this peak on the left is twice as big as the peak on the right, which means that there are twice as many electrons. So we have relative intensities. The bigger the gap between them, the bigger the energy difference between them. So you'll notice that this scale goes from 20 megajoules per mole down to 0 megajoules per mole. This one similar, but you can see a much larger gap here. You'll also notice the small peak and a larger peak, as well as another larger peak. Okay, and we have a relative intensity of 1 and 2. That would not be a good spectrum, but okay, whoopsie. Sorry. So we can see that these electrons require a great deal more energy to remove than these electrons. So the fact that we have this big gap tells us that we have probably a difference in shells here. So when we look at this and we try to analyze what element this could possibly be, we want to think about these relative intensities. We also want to think about these gaps. So we know that this is always going to fill in at, this is an S here, and then we have a gap. And so this must be an S and this must be a P. And so we know that the relative intensity in the valence electrons, I have 2 here and only 1 here. And our closest in core electrons has 2, not 6. So we know that this is not a P. This must be an S orbital. And so it has to be 1s2, 2s2, 2p1. Remember, we fill from lowest energy to highest energy. So this is boron. So when we look at these spectra, it's important to recognize that sometimes the 1s is going to be cut out because it's too far away and it makes the graph too long. Sometimes it's going to be, you'll see kind of a diagonal line, and that's telling you that they've just cut out the section, but it is still going to be the big energy gap. So pay attention to the scale. And you notice on this last one that we went from high energy on the left to low energy on the right. And that's backwards of most graphs. So you definitely have to pay attention. Very often photoelectron spectra are presented this way, but sometimes they will be presented more traditionally with low energy on the left and high energy on the right. So you just have to pay attention to the scale that's given. And remember, ionization energy is how much energy it takes to remove the electron. So outermost electrons require less energy, innermost electrons require more energy. So the fact that this one required 20 megajoules per mole and this one just above 0, maybe half of a megajoule per mole, tells us that these are outer electrons and these are inner electrons. So if we were to look at this one, this is a good example of that cut type of scale. So we can see down here we have 0. So these are the easiest electrons to remove, followed by these are a little harder, these are harder still, and these are the hardest. You notice that this is 104 megajoules per mole. So this tells us that this must be our an s orbital. We know this is an inner orbital. That's an s. Same height, this must also be an s. Triple the height, this must be a p. And then this must also be an s, but you notice that it's only half the height. So we would say that this is a 1s2, this is a 2s2, this is a 2p6, and this is a 3s, but there's only one because it's half as high. So we can start to see how we can take photoelectron spectra and we can determine the electron configuration. So this would be sodium. They show the relative number of electrons and the binding energy. That's the amount of energy that's required to remove the electrons from the atom. The electrons with the highest binding energy are the ones that have the greatest Coulombic attraction because they're the closest to the nucleus. Always, always, always read your axis. So again, you notice that this one, our binding energy, high energies on the left, low energies on the right. These two peaks are the same height. This one is taller. So we're going to assume that this is an S2, S2, P6, S1. And so we have sodium again. Okay, so I want you to think about these questions and we'll go over them in class. I want you to think about where's the highest binding energy on this graph, on the left end or the right end? Which peak represents the 1s orbital? How many electrons are in that 1s orbital? Which peak represents the p orbital and how many electrons are there? What's the electron configuration and what element is this? So let's take a quick look at a sample AP question and then we'll close for today. So here we have two photoelectron spectra. One is of nitrogen and one is of oxygen. And they're showing just the 1s electrons. And it's asking you to explain why the peak in the nitrogen spectrum is to the right of the peak in the oxygen spectrum. And so it's asking you to explain why it takes less energy, because we have to look at our scale, less energy to remove the 1s electron from nitrogen than it does from oxygen. So we'll pick up with this question in class. Think about your answer. And as always, if you have questions, let me know. I look forward to seeing you in class.